So we're going to focus on a set of steps to graphing rational functions. So a rational function, we'll just give you like a little overview. A rational function is usually written, so f at x stands for some function. G at x is some other function, and we'll call it h at x. So it's usually referring to like some function over another one, okay? And this could be like a linear equation, quadratic, quartic, could be all different kinds. So it's like one of them divided by the other one is usually definition. There's another version that looks like this. I'm just going to say a at x. It's called a reciprocal function. And this stands for same idea. It's just some constant value over some equation. It could be linear or quadratic. They behave roughly the same. There's just some specific pieces to this one. It's a little easier to work with. So in this one, if I was to define this as a rational function, I can right off the bat, I'm going to use these letters if that's okay.
Yeah.
I'm going to say g at x. So I'm going to define what it is. G at x happens to be 2x squared plus 9x plus 4. Okay. And h at x is going to be 2x plus 1. So right off the bat, I notice that I have, this would be quadratic because the power of the leading variable is 2. And the other one would be a linear function because the power here, even though we don't write it, is technically to the power of 1. So I have a quadratic divided by a linear. I want to go about graphing it. Looking at it in this way is difficult. This is usually known as the standard form. This one is kind of a standard form of a linear. It's like the slope y-intercept. But what we're going to do is we're going to try to factor them so that they're almost like terms multiplied by each other. And what that'll do is help us find roots or x-intercepts. And then from there, we can find out a lot of information. It's usually one of the easiest ways to graph is finding a bunch of intercepts. In order to do so, I have to factor my quadratic. Okay. So I'm going to work with just g at x to start. We'll write it down here. We'll call it g at x is equal to 2x squared plus 9x plus 4. There's lots of different ways to factor. I'm going to guess that maybe one of the ways you've learned is two numbers that multiply to a times c. Is that that multiply to a times c, which is like 2 times 4? Does that seem familiar? Okay. And then those same two numbers have to add up to whatever our b term is. Yeah, that's common? Okay, so this is 8. So easiest way to do this is try and find factors of 8 because you can find so many values that add, especially once we get into like negatives and positives that add up to 9. But factors of 8 in the style we're using is usually easiest. So 2 and 4 can't really make a 9, but another factor, or the only other factor, is technically 1 and 8. 1 and 8 give us 8, and then 1 plus 8 give us 9. So that works out nice. So we're going to decompose from here. The whole reason we do this is to take this middle term and to split it into two different terms that add up together. So we'll have 2x squared, and then instead of writing 9x, we're going to split it. Positive 1x and positive 8x. And the idea here is 1x plus 8x is 9x. So all we did was decompose the middle. That's why they call this decomposition. From there, you're looking for common factors of the first two terms and the second two terms. Now, how do I know their terms? Anything that has like an addition sign or a subtraction sign splits terms in mathematics. So we have 2 here. If I look at the first one, my coefficients, I can't really simplify. 2 and a 1. I could take a 1 out, but that's not going to change anything. But I do have variables in both of them. And I can take at least an x out. Do you see that piece? That's okay. So we common factor x out of the first two terms, and we're left with this one kind of drops off. We just have a single x, so 2x. And then this is the same as writing just x. So it's like having x divided by x, which would actually just be the value of 1. Okay. Second terms, I don't have variables in both, so I can't factor out a variable, but 8 and 4, I can factor 4 out of both of those. So if I divide both of those by 4, that becomes my common factor on the outside here. And then 8x divided by 4 is 2x, and 4 divided by 4 is 1. So my check here is, are my brackets the same? If they are, boom, I've done it correctly, I'm good. The quick shortcut to this is then to just put those two brackets as a single one, and then whatever is left over in a set of brackets by themselves. Technically, what we've done in this line is another set of common factoring. We've technically factored out this, but that's not too important to know, as long as we're okay with this second step here. So here's our factored form. So now we can go back and rewrite this whole thing. I'm going to rewrite our f of x. And instead of that standard form which we have up here, we're going to write it in, this will be known as a factored form. Okay. So we'll rewrite it as factored form, 2x plus 1, x plus 4. This will make it a lot easier to find intercepts, vertical asymptotes, a lot of things like that. If we take a look, and on the bottom we have 2x plus 1. Whoops, that's the wrong tool. There we go. 2x plus 1. Okay. It looks like we can actually cancel out this value here. Both of them can be canceled out, which would leave this as a linear equation. In other words, what's going to happen is I'm going to go like this. Once you cancel those out, that's like 1 times x plus 4 divided by 1, which is just equal to x plus 4, except that this is a rational function. We know this is not going to come out as a linear. So this tells us something new. This tells us that there's a hole in the graph. And the hole in the graph is at wherever this value in the brackets is equal to 1. Sorry, that's a lie. Equal to 0. So there must be a hole at 0 equals 2x plus 1. Okay, so if we isolate, we end up with negative 1 is equal to 2x. And we get x is at a negative half. So there is a hole in the graph there. So if we were to already start trying to make a rough sketch, we'll put up our little graph here. We'll graph it properly after. There is a hole somewhere along this at about a half. So we'll say 1/2 here because this is our x value and this is our y. I don't know where my graph is at this point. It might be up here. It might be down here. I haven't found anything else out. But I know along here, the graph is going to stop and there'll be some hole. And that's usually how we represent it, as an empty circle. Okay. So there'll be some issue there. Okay, let's go back. What else might we have? So vertical asymptotes. Actually, let's start with a bunch of intercepts and then figure those out after. So usually the next easiest one is a y-intercept. Okay. The reason a y-intercept is easy is because we just, for y-intercept, our step is to set x equal to 0. Okay. So I like function notation because what I'm going to do is I'm going to replace that x with 0 and just plug everything in. If we take a look here, you end up with 2x plus 1. I lied, we're replacing x. So that becomes a 0 plus 1. That becomes a 0 plus 4. This becomes 0 plus 1 again. So let's take a look at what we got. 2 times 0 is nothing, so we get a 1 up top. And then this becomes 4. And this becomes 1 again. So it turns out we have a y-intercept at 4. Okay, so a y-intercept is when the x value is 0 and our y value is 4. So let's go back up to our rough sketch. Take a look. So y is 0 along the x-axis. So that means, I'm not drawing it very much to scale, but let's just assume that is at 0 and 4. So we know the graph crosses there at some point. The next thing we can do is try to find an x-intercept. Maybe I'll go sideways since you usually get landscape paper. Here we go. So we'll rewrite f at x, but actually I should say this. An x-intercept is when y equals 0. Well, f at x represents y. So we're actually going to replace that part. And we'll say 0 is equal to, and we had 2x plus 1, I believe, and x plus 4 divided by 2x plus 1. Okay. Well, we got to find out when it equals 0. One way to look at this is, if I was asking an elementary school student, what's this relationship? Like we have some equation divided by equation. They usually refer to this as a fraction. And for a fraction, there's only one way for a fraction to equal 0. That's if the numerator is equal to 0. Okay? Now, we've already canceled out part of it. Well, we can show both of them here. We have 2x plus 1 and x plus 4. We no longer got to deal with that denominator because it's not important. As long as it's not 0, where that would be undefined, we just need to make sure our numerator is 0. So we're setting both of those equal to 0 here. So in other words, we're really looking at when g at x is equal to 0. That's what's important here. When just the numerator is equal to 0. We got two different values here. So we take a look. We set them both equal to 0. 2x plus 1 equals 0. And x plus 4 equals 0. in this case, we're going to end up with x is equal to negative a half. I know that because we already worked through it a little earlier. And in this one here, x is equal to negative 4. So let's go back. We have x-intercepts apparently at a half. That's interesting. We have 1 at a half. Well, we know that we have a hole there. So maybe the graph is actually crossing, and at that exact spot is where the hole is. We'll go and discover that after, okay? So let's erase this one. We're going to make a little guess at where that hole is. And then x here at negative 4, there's an x-intercept. So let's say this is negative 4. There's some x-intercept here. So we have a y-intercept and an x-intercept. That's good. We also have, let's talk about asymptotes. We have a vertical asymptote, okay? And a vertical asymptote is when, if we're writing it like this, f at x is equal to g at x over h at x. So x-intercepts are when g at x equals 0. Vertical asymptotes are when h at x is equal to 0. So we're looking at h at x equals 0. Well, that's the denominator in our rational function. So when I go take a look at it, if you recall, we'll rewrite the whole thing again just so we know. 2x plus 1, x plus 4 divided by 2x plus 1. Well, h at x, or the denominator, is just the bottom part. So we're setting this equal to 0. So let's set that part equal to 0. We get 2x plus 1 equals 0. Okay. And it turns out that that becomes, we already did this, negative a half. Okay, so this hole also turns out it's going to be some kind of vertical asymptote. It'll never touch that. And we already know that because it is a hole. We're just kind of reconfirming this information. Okay. Now, what we do need to look at is behavior near this. Okay. Near this, what's happening and what happens at the very end value and the end values over here. When rational functions are in certain forms, it's easy to find their horizontal asymptotes, but the form we're in is not as easy because it's like a quadratic over a linear. If you had two linears together, there's a simpler way to find it. We don't though. And if it's a reciprocal, there's an easy way, but again, it's not one of those. So what we're going to do is we're going to talk about this really important piece here. That one and the x-intercept. What is it? Our x-intercept at negative 4 if we remember. Okay. So your teacher may have made some charts like this. We're going to write all the numbers we know from left to right. So if I go as far as I can to the left, I'm at negative infinity. The next major point is at 4. It's not going to be too important for a horizontal asymptote unless there's some very odd behavior, but it's good to put it in. Another one is at negative a half. Sorry, negative 4, negative a half. Oh, was it negative a half? I wrote that vertical one at the wrong spot. Yeah. Oh, okay. It's good we noticed that. We got to go fix that after. And then there doesn't seem to be any other important parts, so we're just going to go towards infinity. And they call this essentially finding like end behaviors. So what we can do, and we can take a look at x values when they're headed in this direction and see what our y values end up becoming. So the question is, what will y become in this case? Okay. So if we're heading towards negative infinity, we could put like a really large number if we want, and it'll tell us what the limit of this value is. In calculus, we get a little more precise about the notation we use, but this is technically a way to suffice. And maybe what we'll do is actually we'll start in the middle too, and then we'll talk about infinities after because they're a little trickier. Let's talk about this one. What's the end behavior around this? Well, we can approach it from two different ways, okay? I can be approaching negative half from the left. So sometimes they'll write that as like a negative. Sometimes write it like this. They'll put like a negative half. And they'll put like a negative in the top right corner. And then they'll have negative a half. Have you seen this notation with a positive of it? And that's essentially the concept of coming at it from the left and from the right. Yeah. So we could split this into two different ones. So maybe we'll do that. We'll split this into two to get an idea of what our y values are going to be. And I'll just move this y down a little bit. Oh gosh. Let's try this again. There we go. Okay. What are our y values? Well, something that's really close to a negative half, but just to the left of it, we can try negative 1/3. That's a little to the... Oh, that's a lie. negative 2/3. That's a little to the left of it. And then a little to the right of this would be negative 1/3. And if we take a look at a number line, we could kind of think of it like this, right? If this is our negative 1/2, okay? What's a little to the right? I know it's hard because it's negative, but we're getting closer to the 0 at a negative 1/3, right? Because this is 0.5, this is 0.33. So that's getting closer to 0 in this direction. And then negative 2/3, that would be 0.66 negative. That's getting closer to negative infinity. So those values work. We just got to remember if we're negatives or positives because they'd be flipped.
I don't know if you're about to do this, but she changes these to decimals.
Yeah, you can absolutely do that.
So she does 0. She only goes down 0.1, so it'd be 0.49, 0.5.
Absolutely. Either of those are good. The closer you get, the more information you have about that end behavior. So, for instance, if 0.5 is our value, if you go to like 0.49999, you can get really, really close. This is a generalization. This might be too far. You're absolutely right. And so the style that she's using where she just goes down like 1/100th of a point, that one works out too. So we can do that. Let's do those values instead.
That's just how she likes us doing it.
Absolutely. Let's do it that way. So let's say negative, in this case would be 0.51, and this one would be negative 0.49 in this case, okay? So what we can do is we plug those into our equation. So if I go down here a little bit, so we're looking at f at negative 0.51, which will give us 2 times negative 0.51 plus 1, and then negative 0.51. I gotta remember this equation here. There it is, plus 4. Okay, remember this was x plus 4 before. I'll write them over top, and this was 2x plus 1, just so we remember. That was our factored form. And then below, we had the same thing below. This will be 2 times negative 0.51 plus 1. Okay. And we're trying to figure out what this will be equal to. At this point, calculator is not a bad choice here. Let me see if I can get us a really quick one. Get a graphing calculator or scientific. There it is. So we're going to put these values in. 2 times negative 0.51. Those in brackets. Plus 1. There we go. That should be in brackets. Get the end quick. There we go. Okay. And then all of this can be divided by the exact same thing. But on top, we also have to multiply by negative 0.51 plus 4, I believe. There we go. We've got our number. Now that we have this in, we'll just replace that value. 3.49 it looks like. So we'll say this is going to 3.49. So it's some positive direction. And if we quickly just replace our 5s in there with 0.49, we can get a much different answer. 3.51. So what might be happening here is instead of an asymptote, what did I say, 3.51? Yeah. What might be happening here is they might be converging at roughly 3.5. And it's coming directly at this. So at a point like this, let's say we aren't sure, we want to take a look. We can put it in a graphing calculator. Now, you won't always have this chance on a test, but let's see if we can make some sense of what it is we're looking at. 2x plus 1, 2x plus 1, and x plus 4. Okay, let's take a look here. At 3.5, is that what the value? Or am I at negative? Should it have been a negative? Should be a hole here. Am I in the wrong direction? All right, let's check this one. Let's see if we can get some real values in here. We said negative, there we go. Oh, negative 1/2. Sorry, I'm looking at the y value. Absolutely. That's the x value we should be looking at. And that is roughly, there it is. There's our hole in the graph, hard to see. Once simplified, you notice that it takes on that linear relationship, which we're going to find out as we go back to this piece. But there's our undefined part. So it looks like they're actually not taking on an asymptote because it's a hole, but they're both converging at a point that just doesn't exist, and then it continues in that same fashion, which we can kind of solve from here. When we go back up, we take a look. We had this intercept of x equals 4. We could go to plot that. We can say f at 4 gives us, I'm going to do this part quickly, 8 plus 1, and what did I say the number is? 4? 4 plus 4 over, oh sorry, it's negative 4. There you go, negative 8 plus 1. Now I'm working in the original here, but we really don't need to do this. These things are always going to cancel out, and really what we're looking at here. Okay, that's an x-intercept, that makes great. We can go down to negative 3.9 if we want, and, sorry, that's on the other side. Negative 3.9, negative 4.1, and look on both sides. But this is an x-intercept. So really, there's most likely nothing's happened here. We're really just looking for values that are undefined. So what's really important here is the end behavior. I put it in here because x-intercepts, what we were trying to do is list all of our key points. But that's really isn't going to be important for graphing because we know this value is going to be 0. We've already solved that piece. What's important here is infinity. Have they given you to just use a very large number?
We do f of 1,000.
Up of 1,000? Perfect. So we can do that too. And negative 1,000, yeah. So let's go over here. So we have space f at 1,000. And we're not going to use that full form. We're going to use a simplified form, right? Which was just x plus 4. We get 1,000 plus 4, 1,004. This is a pretty large number. So we're assuming it's heading upwards, okay? And then f at negative 1,000. We get negative 1,000.
It makes us put in the full thing.
Does she?
Yeah, is that?
No, I mean, you can just, well, I'm going to show you a quick area, 996. The reason that's redundant, I'm going to show you, because I'll show you on all of the ones we've done. The reason it's redundant is because you end up with this.
Like here's like a different version of that.
Yeah. So I'll show you why it's redundant, and we can actually see it. I'm going to go into the scientific calculator. If you notice this piece here, okay, that number is the same as this. And this is a fraction, and they're multiplied. So let's say this calculated into 3. This is 3 times some number divided by 3. Well, you can always reduce a fraction by just dividing the 3 and the 3 and then whatever left over. Okay, so it doesn't matter.
It gives the same answer.
Yeah, you're always going to get those two numbers are going to cancel out. So we did it just to show we were plugging into the rational. But once we got the hang of it, we don't need to plug into that other piece if they cancel out because they're not going to change anything. They'll always end up being a value of 1. So back to this piece, you can write it all out, but you'll end up with this answer both times. It won't make any difference. So what we've got here, we go back up to my graph. Here we go. First of all, I drew that on the wrong side. So I'm glad we pieced that together. Should be at negative 1/2. Negative 1/2. And it looks like we have some behavior, and actually, I should. That's a hole at negative 1/2. We have some behavior that's like a linear function. And if we go take a look at our simplified form, that's what this was. Once simplified, this is all that's left, which is a linear function that just has a hole at the piece that we crossed out. Okay? A heck of a lot of stuff we did. We went through a lot of calculations for that.